The first quantum gas that I would like to consider is a Fermi gas, and in a very special limit, namely in the limit where the temperature goes to zero. The title is a bit sloppy because you can never reach absolute zero, but you can approach zero. We had learned in our general qualitative discussion of Fermi gases that as the temperature approaches zero, the occupation looks as follows. We have a step function. All levels are filled up to the chemical potential and are empty for energies above the chemical potential. Now, as we are in the continuum limit now, I should no longer write Ni for the occupation of the ith level, but I should rather write the occupation factor that we had introduced, F of epsilon. At this point, I'd like to introduce a new concept, the so-called Fermi energy, called epsilon F. The Fermi energy is defined as the energy up to which, at zero temperature, all levels are filled. Now, this is also the chemical potential here. So, at zero temperature, the chemical potential equals the Fermi energy by definition, because the Fermi energy is defined as the energy up to which all levels are filled at zero temperature. At non-zero temperature, chemical potential and Fermi energy are no longer equal. The chemical potential may vary, and we will look at how it varies, but the Fermi energy is always the same. And the Fermi energy, by definition, always refers to temperature zero. There is an equation that defines the Fermi energy, because we have a formula, we have a function that tells us how many levels we have up to a certain energy. That's this curly n. And our requirement says, our definition of the Fermi energy says, that up to the Fermi energy, all levels are filled. Now, we have fermions, so on each level there's exactly one particle. This implies that the number of levels up to the Fermi energy must equal the number of particles. Because we have one particle for each level, all levels are filled up to the Fermi energy. So the number of particles equals the number of levels up to the Fermi energy. Mathematically, this means the number of levels up to the Fermi energy, this is our curly n, equals the number of particles. This is an implicit definition of the Fermi energy. Let's now write down the grand canonical partition function for the Fermi gas at zero temperature, or the log of it. And the log of the grand canonical partition function at temperature going to zero and some chemical potential mu, which in the zero temperature case coincides with the Fermi energy. Remember the general formula? The general formula for the log of the grand canonical partition function is this, you can look at the last but one line, is beta times the integral over all energies, then the curly n of epsilon, times the occupation factor. For zero temperature Fermi gas, the occupation factor is 1 up to the chemical potential, and it's 0 afterwards. So we can simply account for this occupation factor by changing the upper limit of the integral. The integral then only goes up to the chemical potential, up to mu. And then we've automatically accounted for the occupation factor, for the step function. So we can write this simply as beta times the integral from, in principle, minus infinity to mu, but we'll be talking about non-relativistic particles in 3 dimensions, and their energy spectrum only starts at epsilon equal to 0, and therefore the lower limit is 0 up to mu d epsilon curly n of epsilon. So this formula already accounts for this particular shape of the occupation factor. Now, for 3D non-relativistic particles, we learned that the number of levels as a function of epsilon is proportional to volume times epsilon to the power 3 halves. This allows us to calculate the integral from 0 to infinity d epsilon n of epsilon. The n of epsilon goes like epsilon to the power 3 halves. When we integrate that, we get an epsilon to the power 5 halves. So essentially, the n of epsilon times epsilon, and then we get an extra numerical factor, 2/5. And we have to evaluate that at the upper limit, which is mu. So we have a mu times n of mu. And evaluated at the lower limit 0, this simply gives 0. So we have a very simple formula for this integral. And this gives us a formula immediately for the log of the partition function, temperatures approaching 0. This is 2/5 beta mu number of levels up to mu. Again, we can use this as the starting point to derive gas equations. So let us look again at beta times the pressure, which by our general framework is given by the partial with respect to volume of the log of the grand canonical partition function. Again, as in the classical case, the log of the grand canonical partition function is proportional to the number of states up to mu, but the number of states up to mu in turn is proportional to the spatial volumes, proportional to v. So the log of the partition function itself is proportional to v, and taking the derivative with respect to v simply means dividing by v. So this is, once again, as in the classical case, this is the log of the partition function divided by v. We can multiply by v. We find that beta pressure volume equals the log of the partition function. And there we use the result on the previous line, the log of the partition function, that is 2/5 beta times mu, but here we can now say the chemical potential at temperature 0 equals the Fermi energy. So this is the Fermi energy times the number of levels up to the Fermi energy. But the number of levels up to the Fermi energy, by definition, is equal to the particle number. That's what we said on the top right. That's what defines the Fermi energy. Yeah, so this is equal to n. The inverse temperature beta cancels out, and we find that pressure times volume equals 2/5 Fermi energy times particle number. And this is different from the classical case. Yeah, so compare with the classical case. Classically, we had pressure times volume is equal to nkt. This is very different. Especially when you solve this for the pressure, you can say the pressure is equal to 2/5 Fermi energy times particle density, n/v. Or classically, you would have the pressure is kT times n/v. Classically, as the temperature goes to zero, the pressure goes to zero. And at zero temperature, classically, you wouldn't have any pressure at all. All the particles in the gas, they would freeze, and you would have no pressure at all. But in a Fermi gas, you still have a pressure. On the right-hand side, you have the Fermi energy, which can be pretty high, much larger than kT. There's no dependence on temperature that forces the pressure to go to zero. So the pressure can be pretty high. And this is intuitively easy to understand because the Pauli principle forbids that all the particles assemble in the ground state where they would have zero kinetic energy. And then, as in the classical case, they would all freeze, they would stop to move, and you would have no pressure. Due to the Pauli principle, this is impossible, and higher levels have to be filled. So even at zero temperature, levels with higher kinetic energy have to be filled, and therefore you have a pressure. So let me note this here, that you can have high pressure even though the temperature is zero. And this is, by the way, a reason why, for example, neutron stars, which consist of, as the name suggests, neutrons, which are fermions, so you can describe them as a Fermi gas. They are very dense and they are very strong gravitational forces, and you would expect gravitational collapse due to these very strong gravitational forces. But inside a neutron star, there's a very high pressure, and that's due to this effect here, that the pressure of a Fermi gas is very high, even at low temperatures. And this high pressure makes such that the neutron star can resist gravitational collapse. Let's complete our comparison with the classical gas and also calculate the internal energy of a Fermi gas at zero temperature. There are two ways to do that. You can either take minus the partial with respect to beta of the log of the grand canonical partition function, or alternatively, you can do it directly by evaluating the integral over all energies, level density, times occupation factor, but the occupation factor makes such that the integral extends only up to the Fermi energy, times the energy. So this gives you your sum over all occupied levels, or the integrate over all occupied levels, and their respective energies. For a non-relativistic particle in 3 dimensions, we know from the formulas for the level density and the number of states that d epsilon times epsilon is nothing but 3/2 the number of states up to epsilon. So in other words, this is nothing but 3/2 the integral from 0 to Fermi energy d epsilon number of states up to epsilon. So when you integrate that over epsilon, you get a factor 2/5 times Fermi energy times the number of states up to the Fermi energy, which we know to be equal to the total number of particles. So in other words, the internal energy here the 2 cancels, is given by 3/5 Fermi energy times particle number. And again, you can compare this to the classical case, where we had internal energy is 3/2 nkt. Once again, it looks pretty different. And there's this common feature that you find here again, that the kT in the classical formulas is replaced by the Fermi energy. And then there's possibly also a change in numerical prefactors. A last step you can do is you can, once again, as in the classical case, you can combine the 2 equations that we found. We had the equation for pressure times volume, and we had the equation for the internal energy. We can combine these 2 equations, and we find that the internal energy is given by 3/2 pressure times volume. And this is now, interestingly, the same as in the classical case. So this combination, this is the same as classical. This is not a coincidence, and on probably the next problem set, you will derive this relation, and you will find that this is independent of the statistics of the particles. So this holds for bosons, for fermions. Classically, you will prove that this is truly a universal relation that does not depend on the statistics of the particles. We come next to the Fermi gas at still low temperatures, but no longer zero, or effectively zero. Arbitrary, but still low temperatures. What happens then to our distribution, to our occupation factor? When we draw the occupation factor as a function of energy epsilon, then it's still reminiscent of the step function, but we have a softer edge. Looks something like that. We have here the chemical potential mu. The chemical potential is precisely that energy at which the occupation factor becomes 1/2. You see that from the formula for the occupation factor, f of epsilon is 1 over exponential beta epsilon minus mu plus 1 for fermions. When the energy epsilon is equal to the chemical potential, then the exponent, the epsilon minus mu, vanishes. The exponential is 1. So in the denominator you have 1 plus 1, which is 2, and you have occupation factor 1/2. So the chemical potential is precisely where the occupation factor becomes 1/2. There's an alternative way of writing this occupation factor. You can write this as 1/2 minus 1/2 times the hyperbolic tangents of epsilon minus mu over 2 kt. This way of writing the occupation factor makes a symmetry more apparent. You have a symmetry about mu in the following sense. The occupation factor at mu plus some delta, so let us consider here an energy mu plus delta and compare it here to mu minus delta. Well, the mu minus delta will be a little bit smaller than 1. And the symmetry says that the occupation factor at mu plus delta, which is this the length of this red line at mu plus delta, equals the length of the red line at mu minus delta, and this is just 1 minus the occupation at mu minus delta. So there's a symmetry in this sense around mu. Then you can wonder how broad or how wide is this soft edge. You can try to give an order of magnitude for the size of this transition region from occupation factor practically equal to 1 down to occupation factor 0. Yeah? So the width of this soft edge. And one way to do that is you can, at the chemical potential, you can consider the tangent. You can check where the tangent intersects with the epsilon axis and where it intersects with the dashed gray line. These are the two intersections, and the width of this region, of this purple region, this gives you a measure for the width of this transition region. You can easily calculate that using the formula for the occupation factor. You find that the width of this transition region is 4 kT. So as expected, qualitatively, the larger the temperature, the softer the edge, and the wider this transition region. And in the limit t going to 0, you have a sharp edge and the transition region becomes infinitely narrow. Before we delve into the mathematics here, I'd like to make some qualitative statements about the Fermi gas at low temperature. What would you expect physically? How should a Fermi gas at low temperatures behave? Well, one way how you study the properties of a system in the lab is that you subject it to some external action, some external field, or you start to heat it, and you apply some action from the outside to the system, and the system will somehow respond. And you measure the response, and from this response you draw conclusions about the properties of the system. Now, what will a system generally do when you apply some external action to it? Or what can a system do? It can respond by making internal transitions between levels. Yeah? So, let's say I start to heat the system, and this means that particles will jump to higher energy levels. Now, look at this low temperature Fermi gas and look at what possibilities this Fermi gas has to respond to some external action by level transitions. If you're well below the chemical potential, then almost all the levels are filled. When all the levels are filled, they are all blocked, they are all occupied. You cannot have transitions because the Pauli principle forbids to occupy a level twice. And therefore, if all the levels are occupied, then you cannot have transitions. They are all blocked. If you're well above the chemical potential, where the occupation is practically 0 at the moment, then again, you won't have any transitions because there are no particles in the levels that could jump to another level, because the levels are practically all empty. The only region where you can have level transitions is this transition region where some of the levels are filled, some levels are empty, and so if you add a little bit of heat to the system, so a particle would like to jump to perhaps the next higher level, then there is a particle there that can jump, and this particle will find another level that is empty. And that's only possible in this transition region. So this qualitatively suggests that the response of a Fermi gas to some external action is dominated by the particles in the transition region. On the following pages, we'll do a lot of calculations, and for one specific response coefficient, namely the specific heat, we will prove this qualitative statement also mathematically, that indeed it's only a fraction of the particles that actually responds to my heating, namely it's the particles that sit in the transition region. So we consider low temperatures where low means that kT, which is the width of the transition region, is much smaller than the Fermi energy. This is the definition of low temperature. Then the statement was that in response to some weak external action, that could be heating or applying a weak field, you would expect transitions between nearby energy levels. Nearby because the external action is supposed to be weak. But for Fermi gas, you have the following constraints: that far below the Fermi energy, all the levels are occupied and hence blocked by the Pauli principle. So you cannot have any level transitions there because there are no levels to go to. They are all blocked. Now, far above the Fermi energy, there are no particles that could make a transition to a nearby level. So we conjecture qualitatively, and we are going to confirm this mathematically for a specific case, that the response of the Fermi gas to my external action will be dominated by particles near the Fermi energy, that is the transition region. And as I said, that we are going to show this later for the specific heat. Now, in the mathematical treatment of the Fermi gas at low temperature, we're going to need one particular approximation, mathematical approximation, which is known as the Sommerfeld expansion. And it refers to the following. Consider the function that looks like this. So very much like our occupation factor, only that it is shifted such that this half point, or where the value is 1/2, is at x equal to 0. And this is the function 1 over exponential of x plus 1. We can decompose this function into two parts. We can write it as a step function, where the step is at x equal to 0, plus, or the difference between the true function and the step function, and this difference has the following shape. It starts to the right here at 1/2, and to the left at minus 1/2. This function here is it's the sine of x, so this is minus 1 if x is negative, it's plus 1 if x is positive, times 1 over exponential of the absolute value of x plus 1. So this is a way of decomposing the function on the left-hand side. Now let's consider another function, an arbitrary function phi of x. A function phi of x which varies, which in the vicinity of x equals 0 varies much more slowly than the blue function. Now that said, we look at the integral, an integral of the form, integral from minus to plus infinity dx phi of x over e to the x plus 1. We can use the decomposition of the blue function and write it as a sum. First of all, integral dx phi of x times the step function, but the way we can incorporate that is that we say when we have a step function, then the integral ranges from minus infinity to 0 only. This way we've incorporated the step function. Plus integral from minus to plus infinity dx phi of x times this difference sine of x over e to the absolute value of x plus 1. You see that this second part, this correction to the step function, is non-zero. I mean, strictly speaking, it's non-zero everywhere, but it goes rapidly to 0 as you go away from the origin. So on a scale x of the order 1, this correction to the step function approaches 0 rapidly on both sides, to extending to plus and minus values of x. Whereas we said that phi varies very slowly. So in this range where the correction to the step function is non-negligible, in that range we can linearize phi. We can say this is approximately phi at the origin, phi of 0, plus phi primed at 0 times x. It's an expansion around x equal to 0, and we can terminate this expansion after the linear term, because we assume that phi varies slowly. It varies on a scale much larger than 1, so that any higher order contributions to this Taylor expansion become negligible. So we have this expansion of phi of x. We can look at the two terms individually. The first term, the phi of 0, this will not contribute to the integral, because phi of 0 is a constant, which you take in front of the integral, and then you just have the integral over this correction to the step function. But if you look at the curve, there's it's an odd function, so the integral over this correction will give 0. So the first term that's going to contribute is this linear contribution, phi prime of 0 times x. So, in other words, with our expansion, this is the integral from minus infinity to 0 dx phi of x, plus, and then we have phi prime of 0, which we can take in front of the integral. And then we have the integral dx x times this correction. Now x times this correction is an even function. The correction itself is an odd function, x is an odd function. The product of the two is an even function. So rather than going from minus to plus infinity, we can also go from 0 to infinity and then multiply by 2. So we can say 2 times integral from 0 to infinity. And then we can also omit the sign of x, because then x automatically is always positive. So we have x over e to the power x plus 1. Now this is a special integral that you can look up in tables. This is equal to pi squared over 12. And you have 2 times that, so this gives you then, well, the first term remains phi of x, and then you have pi squared over 6 times the derivative of phi at 0. And this approximation is known as the Sommerfeld expansion. And it's a mathematical tool that we are going to use in the discussion of the low temperature Fermi gas. Let's see how this helps us calculate the grand canonical partition function. The grand canonical partition function as a function of temperature and chemical potential is, as before, the general formula, beta times the integral. And here let me be a general and allow an energy spectrum that has the ground state somewhere, not necessarily at 0, so let me write the full range from minus to plus infinity. D epsilon curly n of epsilon times occupation factor f of epsilon. Then we can substitute x. We substitute x as beta times epsilon minus the chemical potential. With this substitution, we can write this as an integral from minus to plus infinity dx. Then this number of states n evaluated at ktx plus mu. So this is the substitution solved for epsilon. Then you find epsilon is ktx plus mu. And the occupation factor becomes very simple with this substitution, because the occupation factor is then just 1 over e to the power x plus 1. And now we have it in the same form that appeared in the Sommerfeld expansion. Some function of x over e to the x plus 1. Now we are looking at low temperatures. T is low, and therefore ktx is small, and therefore the numerator in the integrand varies only slowly with x, because the x has this prefactor kt, and kt is small because we have low temperatures, and hence n as a function of x varies slowly. So we can say that the numerator varies slowly with x, and in particular this holds true near x is equal to 0. And this means we can apply the Sommerfeld expansion. And the Sommerfeld expansion tells us that this integral is the sum of two integrals. The first one is an integral from minus infinity to 0 dx n of ktx plus mu plus pi squared over 6 times the derivative of the numerator at x equal to 0. The derivative of the number of states n is the density of states. So we find the density of states at x equal to 0, but then the argument is ktx plus mu. At x equal to 0, the argument becomes mu. So we have the density of states at mu, and then we have an inner derivative, because in front of the x we have a factor kt, and we have to take into account that inner derivative. This gives a kt. So you see that the log of the grand canonical partition function is now a sum of this first integral plus pi squared over 6 kt times the level density at the chemical potential. And the first contribution we call the log of the canonic of a partition function which we call z0, and the second contribution we call the log of another partition function z1. So the log of the full grand canonical partition function is the sum of the logs of two separate partition functions z0 and z1. Now remember our very general discussion of composite systems. When you have a composite system and you have independent subsystems, then the partition function of the entire system is the factorizes. It's the product of the partition functions of the subsystems. Or if you take the log of that, the log of the partition function of the composite system is the sum of the logs of the subsystems. And you have, at least formally, mathematically, it looks like this here. It looks like you have two independent systems described respectively by partition functions z0 and z1, and the low temperature Fermi gas is a composition of these two subsystems. So formally, you can say this is like two independent systems. So we have the partition function, and we can apply our usual machinery and derive various results from this grand canonical partition function. The first step, we could look at the total particle number. By our general framework, this is given by the partial with respect to alpha of the log of the partition function at fixed beta and also fixed volume. We have to be a little bit careful here, because sometimes we use alpha, sometimes we use mu. So it's important that you don't mix these up. We had written the grand canonical partition function in terms of t and mu, and here we are using again alpha and beta. Well, alpha is equal to beta times mu, and when we keep beta fixed, then a partial with respect to alpha is nothing but a partial with respect to mu with an extra factor beta. So this is the same as 1 over beta times partial with respect to mu of the log of the partition function. And now let's look at our formula. Let's look at our result for the partition function. The first contribution, this integral from minus infinity to 0 dx n of ktx plus mu. We take the derivative with respect to mu. So in the integrand we have the derivative of n with respect to mu. This, however, is the same as the derivative with respect to x, except for the extra factor kt. So we have then, in the integrand, we get the derivative of n with respect to x, and a factor kt, or 1 over kt, and then we integrate over x. This neutralizes the derivative with respect to x, and we are back at the number of levels at the curly n, but we have obtained an extra factor 1 over kt, which cancels with the 1 over beta that we have in front of the partial with respect to mu. So all that is left then is the curly n at mu. It's the number of states, the number of levels up to mu. And now we come to the second contribution. Second contribution here is this pi squared over 6 kt level density at mu. We derive with respect to mu, we get a d primed. And in our formula here for n, we have an extra factor 1 over beta in front of the partial with respect to mu. 1 over beta is kt, so we get an extra factor kt. So we take the result from the previous page, pi squared over 6 kt, but we have an extra factor kt, so this makes kt squared, and then we have d primed of mu. Next, remember the definition of the Fermi energy. By definition of the Fermi energy, n equals the number of levels up to the Fermi energy. So we can replace the left-hand side by the number of levels up to the Fermi energy. We can subtract from that, from the right-hand side, the number of levels up to mu, and write the difference, number of levels up to Fermi energy minus number of levels up to mu, is equal to pi squared over 6 kt squared d primed evaluated at mu. Next, we remember that we are at low temperatures. At low temperatures, the chemical potential will differ little from the Fermi energy. So this, on the left-hand side, this difference between the ends, we expect it to be small because the difference between Fermi energy and mu is small. So at low temperatures, mu is approximately equal to epsilon f, and therefore this is approximately n primed at epsilon f, so we linearize. It's the derivative of the number of states at epsilon f times epsilon f minus mu. But this in turn is nothing but the density of states at the Fermi energy. And on the right-hand side, we have d primed of mu. And again, we say mu is approximately equal to the Fermi energy, and we can say we can approximate this by the derivative of the level density at the Fermi energy. And so the left-hand side is small because we have the epsilon f minus mu in there, and we expect this to be small. On the right-hand side, we have kt squared, and at low temperatures, kt squared is small. So both left and right sides are small. We can solve this for the difference between the Fermi energy and the chemical potential. This is approximately the pi squared over 6 kt squared, and then we have the d primed at the Fermi energy divided by d at the Fermi energy. And this is the derivative of the log of d at the Fermi energy. So far this is general. Now we can consider in particular our non-relativistic gas in 3 dimensions. So we have 3D non-relativistic particles. In that case, we know d, the level density, goes like the square root of epsilon. And this implies that when you take the derivative of the log of d at the Fermi energy, this is 1 over 2 times the Fermi energy. So the log of d is 1/2 the log of epsilon plus some additive constant, and the derivative of the log of epsilon is 1 over epsilon. So evaluated at the Fermi energy, this gives 1 over 2 times the Fermi energy. We can insert this in the formula above, in the line above, and solve for the chemical potential. And then we find that the chemical potential is approximately the Fermi energy. We can take the Fermi energy out in front of a bracket and say that's 1 minus, then we have pi squared over 6, and then from the derivative of the log we get an extra 1/2, so we have pi squared over 12. Then we have a kT squared. Then from the derivative of the log we have a 1 over epsilon f. And since we took an epsilon f in front of the bracket, we get an extra 1 over epsilon f. So we have a 1 over Fermi energy squared. And that's it. This is all this derivation was at fixed particle number and also at fixed volume. The fact that we keep particle number and volume fixed is encoded in the fact that we keep the Fermi energy fixed throughout, right? Because the Fermi energy depends on the total particle number that enters in the definition of the Fermi energy. It also depends on the volume, because the number of states depends on the volume, and that also enters in the definition of the Fermi energy. So what you see from this formula is that there's a minus sign inside the square bracket, so the chemical potential is lower than the Fermi energy at finite temperatures. And the difference between chemical potential and Fermi energy is of the order kT squared. So it grows quadratically with the temperature. At 0 temperature they coincide. At low temperatures there's a difference of the order kT squared. This confirms also our qualitative discussion of fermions. Remember that we said the chemical potential varies with the temperature, and it may even become lower than the Fermi energy. At high temperatures it can even become negative, so it can even become smaller than 0. But for high temperatures this approximation is no longer valid, so the formula from you will have a different form. And next I would like to turn to the entropy of the Fermi gas, the low temperature Fermi gas. This requires a little bit of preparation, and what I'm going to do is I'm going to calculate the entropies associated with these two partition functions, Z0 and Z1, separately. Remember that formally we can view these as two independent systems. Each of them has an entropy, and I calculate them separately and then I add them up. So let me start with the Z0. Associated with that is an internal energy that's minus the partial with respect to beta of the log of Z0 at fixed alpha. What is the log of Z0? Remember the formula, that is beta times the integral from minus infinity to mu But here, since when I take the partial derivative, I have to keep alpha fixed and not mu, I would like to express it in terms of alpha rather than mu. So the upper limit I write not as mu, but as alpha over beta. And then I have the epsilon, number of states, n of epsilon. Inside the bracket I have a product, beta times integral, so I have to use product rule. First I get the derivative of the factor beta, and this just leaves me minus the integral from minus to infinity to alpha over beta, d epsilon n of epsilon. And then I have minus beta times the derivative with respect to the upper bound of the integral gives the integrand evaluated at the upper bound, so n at alpha over beta, times the inner derivative of the upper bound with respect to beta. This is minus alpha over beta squared. You see that one of the betas cancels, and this is it for the moment. This is a result for the internal energy associated with the Z naught. Then let me look once again at the particle number, but now the one associated with the partition function Z naught. So all the quantities that I derive from that get a subscript 0 to make this clear. So this is once again the partial with respect to alpha at fixed beta, and I can use again the form of the integral up there. So I have a derivative with respect to the upper bound up to a factor 1 over beta. So I have beta times the integrand evaluated at the upper bound, alpha over beta, times the inner derivative of the upper bound with respect to alpha. This is 1 over beta. Once again, a beta cancels, and this is simply the number of states up to alpha over beta. Now we are ready to calculate the entropy associated with this fictitious subsystem naught. This is the log of the partition function Z naught plus beta times U naught minus alpha times N naught. That's our general formula, how you calculate the entropy from a grand canonical partition function. The log of the partition function, this is beta times the integral from minus infinity to alpha over beta, d epsilon n of epsilon, plus beta times U naught. U naught, we see up there, has two contributions. The first contribution is an integral minus, then we have a beta in front, and then integral from minus infinity to alpha over beta, d epsilon n of epsilon. You see immediately that these two contributions cancel. Then from the U naught, there are two minus signs there that cancel each other, so we have a plus. Beta times the expression up there. The expression up there has a factor alpha over beta. The beta cancels, and what remains is the alpha. So we have alpha times n evaluated at alpha over beta. And then finally we have the contribution from the minus alpha n naught. We have minus alpha n naught, but n naught we found to be the number of levels up to alpha over beta. And you see that these two terms also cancel. So the entropy associated with the partition function Z naught is actually equal to 0. Intuitively, this is not too surprising, because from the form of the partition function you see that this corresponds to a step function with all levels filled up to the chemical potential and all levels empty above that. So this corresponds to the situation at zero temperature, where the entropy is also zero. Let's now turn to the other contribution, the contribution from the grand canonical partition function Z1. This had the form pi squared over 6 kT times the level density at the chemical potential. As you saw on the previous page, we are going to take a lot of derivatives with respect to alpha and beta, so I would like to express this in terms of alpha and beta, and hence I write it rather as pi squared over 6, kT is 1 over beta, and mu is alpha over beta. Then, again, let's look at the internal energy minus the partial with respect to beta at fixed alpha. Product rule, we have first the derivative of the factor 1 over beta. This gives us minus 1 over beta squared, but then we have an overall minus sign when we calculate the internal energy. So this minus sign cancels, and we have pi squared over 6, 1 over beta squared, level density at alpha over beta. And then we get minus pi squared over 6, 1 over beta. And then we have the derivative of the level density times the inner derivative of the argument, and this is minus alpha over beta squared. And I'll leave it at that. Maybe the only thing I can do is to cancel the two minus signs. This gives effectively a plus. Then we turn to the particle number, n1. This is the partial with respect to alpha at fixed beta. This is pi squared over 6, 1 over beta, the derivative of the level density times the inner derivative of the argument with respect to alpha, which is 1 over beta. Then we have all the ingredients to calculate the entropy. It's the log of Z1, again the general formula, plus beta times U1 minus alpha times N1. Let's add up the various contributions. So the log of the partition function is pi squared over 6, 1 over beta, level density at alpha over beta. Then we have plus beta times U1. There are two contributions to U1. The first one multiplied by beta gives pi squared over 6, and then we have a 1 over beta only, and we have level density at alpha over beta. Then we have pi squared over 6. The prefactor beta cancels with the 1 over beta. We have d primed at alpha over beta, and we have an alpha over beta squared. And finally, we get minus alpha times n1. The n1 again contains a pi squared over 6, contains the derivative d prime at alpha over beta. It contains a 1 over beta squared, and we multiply this with alpha, so we have an alpha over beta squared. And luckily, these last two terms cancel, and you see that the entropy, and the first two terms are identical, so the entropy is given by pi squared over 3, 1 over beta, which I now write again as kT, times the level density evaluated at alpha over beta, which I now write again as mu. So we have a formula for the entropy associated with this part Z1, and the total entropy of the Fermi gas is equal to this S1 because the S0 was 0, it didn't contribute. So the total entropy S is simply equal to S1. We have not specified the level density yet. We can do this now. Again, we look at non-relativistic particles in 3 dimensions. Then the level density goes like the square root of epsilon, and it's easy to relate the level density to the number of states. This is 3/2 times the number of states up to epsilon divided by epsilon. We used this before, this relationship between n and d for non-relativistic particles. This allows us to write the entropy S in this form. We had pi squared over 3 kT. Now, previously we had on the left-hand side S over k. Now I take the k on the right-hand side, so we get a k squared T. And then we get the level density at the chemical potential, which I now replace by 3/2 number of states up to the chemical potential divided by the chemical potential. Factor 3 cancels. And now at low temperatures, that's the regime in which we're operating. At low temperatures, we remember that the chemical potential is approximately equal to the Fermi energy. So in this approximation, the entropy of the Fermi gas becomes pi squared over 2. Then we have a k squared T over mu. I'd like to split this into kT and an extra factor k. And I would like to say that the chemical potential is approximately equal to the Fermi energy. And then we have finally the number of states up to mu. If we replace mu by the Fermi energy, it's the number of states up to the Fermi energy, but by definition, the number of states up to the Fermi energy is the number of particles. So this is n. Yeah? So this comes from the number of levels up to the Fermi energy. And here you see something interesting that links with the general remarks that I made in the introduction, that you have here a factor, a ratio, kT over Fermi energy. This is a measure for the fraction of particles in the transition region. Now you remember the transition region had a size, a width of the order kT. The range where you have occupied levels has the size of the order of the Fermi energy. So the ratio kT over epsilon f over Fermi energy is a measure for the fraction of particles that are in the transition region. So already here you find the result that a certain thermodynamic quantity, namely the entropy, is dominated by the particles in the transition region. Again, this is intuitively clear because outside the transition region, sort of for lower energies, for energies much lower than the Fermi energy, all the levels are occupied, and so you have, in this sense, maximal order and no entropy. And far above the Fermi energy, all the levels are empty, so there's no entropy there either. Only in the transition region do you have uncertainty about whether a level is occupied or not, and therefore only in the transition region you expect a contribution to the entropy. So conclusion, the entropy is dominated by particles in the transition region. I had promised to you that we would look at one specific response coefficient of the low temperature Fermi gas to verify this claim that the response of the system is dominated by the particles in the transition region. And the response coefficient that I would like to look at is the specific heat. The specific heat at fixed particle number and volume. You discussed in your last homework that the precise definition of the specific heat is temperature over particle number times the partial of the entropy with respect to temperature at fixed, in this case, particle number and volume. As I said before, keeping particle number and volume fixed is implicit in keeping the Fermi energy fixed, because the Fermi energy depends on both. We saw on the previous page that the entropy is simply proportional to temperature. So taking the derivative with respect to temperature is the same as dividing by temperature. This cancels with the temperature in front of the partial, and so this is nothing but the entropy divided by particle number. We use the general formula for the entropy from the previous page. We find this is pi squared over 2. We have this factor kT over Fermi energy, and we have a Boltzmann constant, and the n drops out because we divide by n. So once again, we have in the formula for the specific heat, we have this fraction, kT over Fermi energy. So once again, the specific heat, which characterizes the response of my system to the supply of heat, is dominated by the particles in the transition region. That effectively only the particles in the transition region take part in the response to this external heat supply. And that is precisely what we had expected qualitatively. Just for comparison, look at classical gas. In a classical gas, the internal energy is given by 3/2 nkt, and the specific heat classically equals 3/2 times K. So it's independent of temperature, whereas the specific heat of a Fermi gas, a low temperature Fermi gas, is proportional to temperature. So at low temperatures, the specific heat of a Fermi gas becomes very small, whereas the specific heat of a classical gas is unaffected by a change in temperature. So what you can, this is just a specific example. You can do similar calculations for other response coefficients, and what you find is that effectively the number of degrees of freedom of your system is reduced by a factor kT over Fermi energy. And this reflects the fact that the transition region dominates the response to whatever external action you apply to the system. So quite generally, you can say that effectively the number of degrees of freedom in a low temperature Fermi gas is reduced by a factor of the order kT over Fermi energy. And the remaining degrees of freedom are, if you wish, they are frozen by the Pauli principle. All the other particles, they are blocked, they can't move, they sit where they are, and in a way they are frozen in and they cannot participate in the response of the system.